Good morning, everybody, and welcome to the third week of Physics 3, I'm sorry, okay? And we are still dealing with the topic of thermodynamics. So far, what we have seen is the Zeroth Law of Thermodynamics, which was really a way to help us define temperature and actually measure it more so than defining it. And it was chapter 18 later on that basically gave us what the temperature was. We built a theory around the idea that the gases are made up of tiny particles, extremely small. And we made some assumptions and we came up with the understanding that the average kinetic energy of those tiny particles is really what the temperature is, with varying constant, of course, KB, which was a very tiny number. So this is basically what the idea that we built so far. We're going to continue on this. We're going to introduce a concept of internal energy, and then we're going to finish the whole topic with the second law of thermodynamics, which is coming next time, which is in chapter 20. Let me first of all put something in here so that I can see what's going on, because this thing keeps going on and off in here. And for some reason, there are quite few who are not here. Not quite few, about 2 people, I think, who are not here, or 3. And of course, this session is recorded and it's going to be posted to the earliest convenience, hopefully today, and so that you guys can basically follow the discussions and post your comments in the appropriate place. Word of caution, excuse me, we're coming to February 5th, which is this weekend. A lot of assignments are due by this time. So please pay attention to your assignments. You really don't want to miss on anything. I know a lot of you submitted the discussion for first week. Some of you have even done the second week. You still also, a lot of you submitted your labs. There was only 1 or 2 people who did not submit lab 1. And also we have the homework assignments on piercing, which are also due. So we have quite a few assignments that are due this weekend. So please make sure that you're on top of them. And also we have an exam toward the end of this month. So the 4th week of February, we will have the first midterm. Let me give you a warning in here, or a word of caution, I should say, about this topic. Thermodynamics, some of you have seen it in chemistry, and you might be tempted saying, okay, I have seen it in chemistry, I know a lot about it, so I'm going to postpone doing these assignments to later on. And then once you start working on them, you see that they are different than what you have been used to in chemistry. These are actually different perspective. This is the foundations. These are the physics part of it. This, if you wish, the chemistry part of it is just applications of these ideas. That's one thing. And the other thing also that we're gearing toward completely different direction from the chemistry. We're going toward engines and we're going toward heat, basically pumps. And those are not in chemistry. Those are applications in engineering at best. So there is different direction we're taking. So you might get back into those assignments and submit them as soon as possible. Hopefully this is clear. And everybody is on board as far as this issue, okay? So this is, in general, basically where we stand. Let me share with you the screen to help basically put everything together to move on from this point on. So let me share my notes, share button, okay? Now, again, I have had problems with Tuesday sessions where the internet drops for some reason. If it does, please do not leave. I will try to reconnect as soon as possible, okay? So, chapter 19. Let me summarize again what we did so far. Chapter 17, really, all it did was introduce to us the first law of, or the zeroth law of thermodynamics, and that allowed us to measure the temperature T. Chapter 18, we were able to find an idea that the average kinetic energy per molecule, this is again translation, per molecule, is nothing but related to, I mean, there is a constant in here, so there is a constant, if you wish, times T. Okay, so the temperature itself that you measure with the thermometer per chapter 17 is nothing but that average kinetic energy per molecule. okay? So that's the model that we built. And then we geared toward the statistical approach, basically, to describing this thing without using a lot of the verbiage used in statistics. There is something that I try to avoid, but it's probably time to say it in name, the function f that we talked about it, f of v dv, in the distribution of the velocities between v and v plus dv. That has a name. This is the probability density function. The function itself, probability density function. And this is the one that we studied extensively, okay? Furthermore, the most probable velocity has a name. This is called the mode. In other words, if I take particles at random, most likely this is what I'm going to find, the most probable velocity, which is the mode of this distribution. So this is basically ideas from statistics, and without really, honestly, justification, if you wish, we introduced this function f. There is a lot of buildup in statistical mechanics towards it to arrive at its form, okay? So we just put the function f, which has that Gaussian-looking distribution, except that it was weighed by a factor of v squared, and then we dealt with it. Another word of caution in here, when you deal with this function itself, when you deal with the Gaussian, it has to do with something else called the gamma function. So I'm just basically trying to say things that probably you might come across it, and so that you're not too how should I say, too surprised. So the Gaussian itself that we discussed last time has to do with the gamma function, and the gamma function is an extension of the factorial function. Okay, this is just an extension of that. I mean, factorial of 2 is 2, factorial of 3 is 6, and so on and so forth. But factorial of 1/2 is actually exactly square root of pi. Okay, or is it square root of pi over 2? One of them. It has to do with the Gaussian. It's exactly the Gaussian function. So that is really how some of the things that you might encounter. Once you get that route, there's all kinds of other functions that might pop up in front of you, beta and other things. So we're not getting into a lot of this detail, but just because of the fact that we introduced this function last time and we dealt with it extensively, and even I shared with you a file that has a lot of those calculations related to the topic. But again, you might look in other references and you might encounter this thing. So don't be too surprised, because the realm of these things is all related in there. Okay, so this is where we are so far. Okay. Chapter 19 now goes back to the energetic or the energy interpretation of thermodynamics, okay? We're not gonna be using a lot. I mean, we know what the temperature is. That's basically from chapter 18, but we're going to go back from an energy perspective. So we're dealing with an ideal gas, okay? And an ideal gas meets requirements in terms of its density, in terms of the fact that the particles are not interacting, okay? That makes it. The ideal gas obeys this law. And we found its form on the microscopic level, okay? We found that this R is related to KB in a sense that R over Avogadro's number is that constant that Mr. Boltzmann actually used. Okay, he did not really introduce this one, it was introduced by Mr. Planck. Anyway, the point is, there is a macroscopic explanation for this expression in here, okay? In the book, there is actually, when you take into account the interactions of the different molecules, because as, for example, an oxygen molecule gets near another oxygen molecule inside that, even though we're calling it an ideal gas, when they don't interact, there is a small interaction. If you make corrections to that, PV equal to nRT is no longer true. So there is a correction to the pressure because of that repulsion between the two molecules. So P gets less, and the entire volume where the entire gas is occupied is reduced also by a factor that has to do with where those molecules are located, because we're assuming that they are point particles, but in reality, they are not point particles, they have a finite size, okay? So that's So the law PV equal to nRT is not exactly correct for a non-ideal gas. So if you wish, this ideal gas is not real. Okay, it's more like a hypothetical system to help us understand these things. However, when you do calculations, you will find that the error usually even within a few percentiles. Even if you take the interactions into account, even if you take the size of the molecules into account, the mistake that you're going to be making basically is of the order of 2 to 3% of overall. So it's still a reasonable, good approximation for real gases. Okay, so this is something that you have to take into account. Now, because of this law, I have the unknown pressure. I have the unknown volume. I have the unknown temperature. In all of our processes, we're going to assume that N is fixed and R is constant. Okay. N is not fixed in few cases. When chemistry is involved, the processes will involve transformation of one material into a different one. So the number of moles of one basically species of materials will change to a different species, and then the number N changes on you. When chemical reactions are involved, you have a problem. When also phase transformations are involved, you also have a problem. You're dealing, for example, with a gas vapor, and then all of a sudden the temperature drops to below to such a level, and then all of a sudden that gas is gone because it transformed to a fluid. So in this case, there is also a problem with N. So we're assuming that we're far away from phase transformations and also from chemical reactions where this N is fixed, okay? Otherwise, we have a problem to deal with in addition to that. So we're dealing with basically pressure, volume, and temperature. For that, we're going to have a PV diagram. I'm sure you have seen it somewhere in chemistry too, for some of you who took chemistry. So the x-axis is the volume, and the y-axis is the pressure. Okay. If you ask me, on any given point on this PV diagram of a given volume, V is known. Let's call it V naught, and the pressure is known. It's P naught. So you're wondering what is the value of the temperature? I can tell you the value of the temperature at this point is just given by T naught equals to P naught V naught over NR. R is constant, N is assumed to be fixed, the number of moles. So if I know P naught and V naught, I already know the temperature, given of the fact that I'm dealing with an ideal gas, okay? So these three quantities are called state variables. State variables so far are the pressure, the volume, the temperature. Meaning on every given point in the PV diagram, I know exactly these three quantities, all of them, okay? Furthermore, the energy also is a state variable, okay? Meaning, because of how the temperature and the energy are related, and if I assume that there is no potential energy because of the fact that this is an ideal gas, all the molecules are non-interacting, so the only energy I can account for is the kinetic energy, then in this case also the energy is a state variable, even if the particles are interacting. So in this case, I know their distances because of their positions, I can calculate the potential energy. It's still then the energy is still a state variable, meaning it's known exactly for every given point in space. Since I know the pressure, since I know the volume, since I know the temperature, I also know the energy. So these are state variables so far, meaning they are known exactly for every given point on this PV diagram. There are not two of them in that point. There is only unique value in there. That's why they are called state variables. Okay. This is similar to what you guys did when you did physics 1, when you were saying, okay, the position of the particle on a given point in space is given by the vector position R. So R is a state variable. Of course, the velocity, which is a derivative of that r, is also a state variable. It turns out the kinetic energy also is a state variable. The kinetic energy, which is 1/2 of mv squared. Since you know the mass, you know v, so this is also a state variable. U is the energy, the internal energy. That's a good question. Okay. I'm not using the letter E because the letter E is usually reserved for the energy that is due to interacting systems with other systems and things like that. That's how the book uses it too. And that's how thermodynamics defines the internal energy. Does this answer the question? Okay, very good. So again, I'm just drawing a comparison with what you have seen in mechanics. These are also called state variables, including the kinetic energy, by the way. And the potential energy also is some function of R. Okay, that too is a state variable. The momentum also is a state variable. So all of these things were state variables when you're dealing with it, except the work, which was not a state variable. It depends typically on the path that you take. Work is not a state variable. It depends on which way you go from state to state, from point to point in space. So the work typically is not a state variable. Okay, because it depends on the path. It's transition going from point to point in space. Okay, that's what work is. When you have a friction, you have a problem there. So that is a discussion that you have had, I'm sure, in physics 1. So this is a similar, and actually in physics 2 also. Physics 2, when you are dealing with the electric field, the electric field is defined in space, the magnetic field is defined in space. But then in the case of work in there too, which is the potential energy, turns out to be actually also a state variable in that case. But when you're dealing with work, especially when you have friction involved and you do have actually dissipation in that case too, then in that case, that is not a state variable. That's a transition value. Depending on how you go on the circuit, you will make assume one side of heat more so than the other side, depending on the resistor, because the resistor is always wasting energy. So this is just a refresher on those ideas. Okay, here is the point for chapter 19. I'm going to go from this point in space to this point in this PV diagram, point B, that has a different value for the volume. I probably should put this one A instead of not, okay? This becomes a TA now, and this becomes a VA, and this would be PA, okay? So I'm going to a different point in the PV diagram with different pressure and different volume that may not be the same. Okay, the temperature also may be different, okay, which is in this case is going to be PB VB over NR. Okay, so this is basically the essence for chapter 19. The question that we typically ask is how much work did the gas do, because we're assuming we're dealing with an ideal gas, or was done on it. If the number is positive for the work, that means it's energy added to the gas. If the number W for the work is negative, that means it lost energy in that form W, okay? So that's the question. We want to find how much work is done either on the gas if W is positive, or by the gas if W is positive. I mean, if W is negative. So if W is negative, it's lost energy in the form of W, So this is the case. If W is negative, that means delta U is negative. That means we lost energy in the form of work. Or if W is positive, that means the energy has gone up by this amount. That means we did work on the gas. We added energy to it in the form of work. So that's question number 1. There is another question that might also help us understand what's going on with the system and going from point A to point B is also the heat. Those are not state variables, by the way. They depend on a process, on going from A to B. depending on the path you take. How many paths can you take from A to B? I'm asking a question. How many ways can you go from A to B?
I mean, as many ways as you want, really.
Infinite number of ways. That's a correct question. So there is possibility for having an infinite number of W and Q. Okay. Does this make sense to everybody else also? Yes.
Yes.
Okay. So it's reasonable. I mean, can think of any number of points that you can pass through. That's also another way of going from A to B. Q also of interest, and that is the heat. So again, if Q is negative, that means we extracted heat from the system. That means the energy went down. Okay? Like what you do when you put food that is warm inside the refrigerator. You're removing heat from it to become cooler and cooler again. Okay, so that's exactly what you're doing. So you're extracting heat. So the refrigerator, what it does, it takes heat from the food or from your whatever you want to cool, and then later on you take it, you find its temperature went down. So its energy went down. Or you could end up with a situation where you pump heat into it. You add heat into it. That too will raise its temperature. So that is actually delta U is going to be positive. Okay. So you end up with more energy in the system if you pump heat in it. Okay. Of course, you might end up with a scenario where in this case, W stays 0. You can go from A to B potentially, depending on where A and B might be, where there is no work added at all, or done on the system or done by it. Same thing. You could end up with a scenario where there is no heat exchange. All you have to do is take your entire system and wrap it in a nice blanket so that it doesn't lose heat or gain heat. Okay? So there is those possibilities too. So those are the ways to change the heat of the system, change the energy of the system, which brings me to the first law of thermodynamics. First law of thermodynamics says the following. Delta U equals to Q plus W. To change the internal energy of the system, either add heat to it or do work against it, or both. Assignment number 1 for today, put it in your own words. Obviously, if you extract heat instead, or you have the gas do work on the environment, then in this case, the delta U is going to be negative. You lost energy. Because this expression is algebraic. This is what I mean by algebraic. That W can be positive or negative, Q can be positive or negative, or they can be 0. Okay. For some reason, I ended up with this thing in here. Okay, so hopefully you guys don't have that extra dot in there. That's a delta U. That's a change in U. Okay, remember, I have a new position in here. I have a new U also. So this was UA. And now I have UB. So what I mean by delta U is really UB minus UA. That is what I mean by it. Like you did in physics 1, you really don't care where the energy, the origin of the energy is. All you care about is the change in energy, potential energy. This is in the same sense. We really don't really care for what the value of the energy on a given point on the diagram is. We only care at the end of the day in the difference of energy. That's all. That's why most of the times we don't care for the value in a specific point A or a specific point B. What we care about is how much, when going from point to point on the PV diagram, how much did we change energy? Okay, so this is really what we care about, is the difference or the change in energy. Okay, so in other words, this is my own way of saying the first law of thermodynamics is to change, to increase the internal energy of the system, either add heat to it or do work against the system. Okay, now if you look at the book, you're going to find a minus in here. Okay, in all the thermodynamics books, you will find a plus. And it makes more sense, honestly, to put the plus there. Okay, so if you look at the book, and even if it's sometimes in the lab, you might find a minus in there because they're assuming that the W is going to be negative, and it really doesn't have a good explanation. Okay, no matter how much I tried to justify it in the past, I abandoned it and went to the standard definition of the law. So the law says, if you want to add energy to the system, all you have to do either add heat to it or do work against this, the gas. That's it. Okay, so that's my own way of saying it. Of course, you can say it that way as long as you have an understanding for it. That's it. That's all you have to do, okay, to add energy to the system. Obviously, this is an algebraic expression. So W could be positive, could be negative, could be zero. Q could be positive, could be zero, could be negative. So now it's a matter of adding all of these numbers and where the thing lands. Okay, if delta U turned out to be positive really, then the temperature must have gone up. If delta U turned out to be negative, then delta U must have gone down. Okay, so that is really in a nutshell what the whole idea is. Does this first law make sense to you guys so far?
Yeah, it does.
Okay, very good. Somebody else also confirm?
Yes, it does.
Yeah, it does.
Very good. So now you're going to put it in your own terms, and we're going to see exactly where the minus sign, the discrepancy between the book and this way of presenting it is going to come out. So the first thing I'm going to deal with is W, the work. Okay, so we're going to find the work. So let's imagine together that we have a gas inside a cylinder of cross-section A. So this is a cylinder. And I have a piston that is impenetrable. That means the gas cannot escape from it. Remember that N, we don't want N to change, okay? I have in here N moles of an ideal gas. So there is a piston in here. This piston can go up and down, okay? So there's your piston in here. It can go up and down. Imagine with me that somehow the gas expands. So the gas expands. So it was at this height. Why? Now it has increased by an amount delta Y or dy. So the new position of the piston, if you wish, has gone up. So the volume of the gas has gone up. So dV is now A dy. So this is the increase in volume. This is not the new volume. This is how much the volume went up because I have cross-section A, and now I have increased by dy. Obviously, dy is an infinitesimal value. So at the end of the day, I'm exaggerating the picture in here, okay? So this is a very tiny value. So the piston went up, okay? The pressure by the gas, which we draw it as an arrow, but it's not a vector, by the way. The pressure is a scalar, okay? So this is the pressure. So the force now, which is a scalar, which is a vector, is actually equal to the pressure times the area. So this is the force, okay? This is how much force is exerted on the piston by the gas. So PA is the force exerted by the gas on the piston inside the cylinder. Okay. And if you guys remember from your physics 1, the work is just force times displacement. Okay. Here is the problem though. I'm going to assume that this is extreme because of this PV equal to nRT. This PV equal to nRT is only true when we have thermal equilibrium. Otherwise, this is not true. When we don't have thermal equilibrium, T can be fluctuating every which way. So we want to retain this relationship in here, PV equal to nRT. So we have to do this process extremely slow. In other words, we have to do it very, very carefully so that at any given time, there is a balance between the force retaining this wall, F, this is the external force, okay, and the pressure from the gas. So when we move it, we have to move it extremely slow. Why? Because we want to make sure that PV equal to nRT at all times. Okay, so this force F, which is exerted by the external agent, is actually equal to the negative value because it's opposite to this one, to retain the piston in equilibrium. Because if there is any imbalance in the pressure in here, the piston will move. If the pressure outside is less than the pressure inside, the piston will move on its own upward. If the pressure upward is more than the pressure inside, then the piston will go down. So you have to know that. So the only reason why it's retaining its position to begin with is there is an external force to keep it so that the two pressures are balancing each other. Otherwise, the imbalance of pressure would cause it to move. That is basically from physics 1-2. Okay, so the fact that it has moved this way is against the external force in here. So in this case, the work is equal actually to, I'm going to write it as dW as the force in magnitude, which is just PA, times the displacement, which is dy, and this better be a negative value. Why? Because I'm actually doing work against the environment. When the piston went up, the energy of the system went down. Remember this tally? Delta U, I'm assuming that Q, there is no heat source or anything like that. Okay, so in this case, the energy must come from somewhere. The work that we're doing must come from somewhere. Okay, there is no free energy whatsoever, and the only place that it can come from is from the inside of the system. So this is how much work is done in this case. I'm going to write it symbolically as minus P, which is the pressure. Well, A times dy is nothing but dV. That's how much work is lost, how much energy is lost when the gas expanded. If the gas went down, if the gas was compressed, on the other hand, if compressed, instead, then how much energy it went up? It's the same amount, minus P dV, because dV is negative now. When it's compressed, dV is negative. The volume went up, shrunk by dV. Then dV is negative, times another negative, that's positive. So the energy, so this is a minus still. So the energy goes up in this case. So in either case, in this infinitesimal process, the work is minus P dV. If dV is positive, that means the gas expands. And when it expands, it moves stuff. This is what I mean by doing work. You could have something in here you want to lift. You could have a car in here probably or something. You would want to lift it. You would want to do work against it. So that energy that we just computed, the work that is done to do work against the environment, must come from somewhere. And the only place that is going to come from is the internal energy of the gas. So this number better be negative. If dV is positive, this number better be negative. Now, if somehow the other way around, you're thinking about how about if we compress it by dV? Well, in that case, the volume shrinks by dV. So the volume is negative. I mean, the change in volume is negative, I should say. The change in volume is negative times the other negative makes it positive. So we're adding energy now to the system. So the environment is the one that is doing work on the system. Does this explanation make sense to you guys? With the negative sign?
Yeah, it does.
Wait, so it's a negative sign if it's compressed or if it stretches out?
It's in either case. There is a negative. Here is the two scenarios. Let me explain them a little bit. If dV is negative, that means we're shrinking the volume. We're making it less and less. Okay. So in this case, dW is positive. Because you have a negative in dV times another negative makes it positive. So we're adding energy in the form of dW. Now, if dV is positive, that means the gas is expanding. Okay, it's growing. So the volume is increasing. Then in this case, dW is negative. Why? Because you still have that negative to take care of the business. So the gas is expanding. That means it's doing work against the environment. Okay, so that energy must come from somewhere. It must come from the internal energy of the gas. So yes, it has to be negative. So in this case, that's how much work is done. So in both cases, I have to have the minus sign. Was it Peyton who asked the question or somebody else?
That was me.
Okay. Does this make sense now?
Yeah.
Okay. So always there is negative. If dV is negative, so be it. If dV is positive, so be it. The number at the end will tell you. So in general, the work is going to be minus the integral from the initial position to the, let's call it A, and call it B, of P dV. The reason why I cannot take P out of the integral yet is because P might depend on V. Remember, P is equal to nRT over V. There is already a V in the denominator, but this T may or may not be constant too. So that's why I cannot take stuff out of the integral. P typically is a function of V in the PV diagram. Okay, so I cannot really pull it out of the integral yet. So it may be a function of the volume. So that's how much work needs to be done from every process that you might think of. Now, the book puts a plus sign in here and try to some sort of a convoluted way explain this thing honestly. And then since they put a plus sign in here, they go back into this law and they put a negative sign. That's not how the standard thermodynamics books do it. So I'm going to stick to the convention that I know you're going to find somewhere else when you read, and that is delta U is equal to Q plus W, add heat, add work, or do work against the gas, delta U will go up. You're wondering in here how much the work is, it's the negative of PdV. That's it. If dV is negative, that means you're doing work against the gas. The negative times negative will be positive. Take care of business on its own. If dV is positive, that means the gas is expanding, doing work against the environment. This whole number will be negative. Takes care of itself. So let's do examples. I mean, if we don't do these things, it's going to be just talk in the just talk basically. Let me go back into this processes in here and try to explain them. I'm going again to the PV diagram. So the pressure is always in the y-axis and the V is in the x-axis. So again, I have starting from point A to point B, how many ways can we go? I'm going to take a simpler case of this all. First of all, to go from A to B, that's called the process. One or more processes, one or more processes, okay? The exception is when A ends up to be A itself. That's actually called the cycle. So if my starting point is my ending point, then I have a cycle. Cycle can be traversed into two different ways, either counterclockwise, and in this case, like this. No, this is clockwise actually. So this is counterclockwise. If we do it this way, the work will be positive. Okay, and if the work is positive, then in this case, we're doing work on the system. Okay, the system is not doing work, we're doing the work. Or clockwise, the way I initially described it. So the first process will be going up. So this is counterclockwise. This is where W is going to be positive. The second case is going in the opposite direction, where W is actually going to be negative. So this is a case where W is going to be negative. This is an engine. Because you would want the engine to do work for you. So W better be negative, better be losing energy from the system. The system must be doing work for you. So that's why it's an engine.
Is the clockwise, well, okay, counterclockwise is when the work is what?
Positive.
Oh, okay.
That's a heat pump, refrigerator, AC unit. Okay. That's a heat pump in general, okay? Let's put it this way, heat pump. Okay, when W is negative is the one that is, the reason why it's an AC unit really is you have to put work on the system to extract heat from it. Okay, that's basically what the process is. That's why it's called the heat pump, okay? Which is an AC unit or refrigerator unit. Work, W better be negative. That means the system is doing work on the environment, okay? That is when dV is positive. When dV is positive, W is negative, okay? That is basically why it's an engine. That is if the starting point is the same as the ending point, you have a cycle, okay? Otherwise, you have a process or more than one. So let's do some typical processes. 4 processes. As you.
Thank you.
Okay, so let's talk about 4 processes. I'm going to talk about these 4 processes in this order. The first process is an isothermal process. In an isothermal process, the pressure and the volume change in such a way that my initial point in here, VI, and my initial pressure in here, PI, and my final point in here, VF, and my final pressure, PF, fall on the same temperature, T. T is constant. Okay? So in other words, PI, VI is the same as PF, VF. It's the same nRT. The temperature doesn't change. T is fixed. That's what an isothermal means. That means delta T is equal to 0. From the picture I drew it, it's not always the same. It's not always the case. From the picture I drew it, VF looks bigger than VI. So W better be negative. Okay? So that is clear. W better be negative because we just made the big argument for it. Okay. Since delta T is 0, this is a big deal, okay? Delta U is 0. So in an isothermal process, there is no change in the energy. The energy here and the energy here, it's the same. So the difference in energy is 0. Why? Because remember, we argued in general the energy is NCV delta T no matter what. Okay? Since delta T is 0, this better be 0. Period. End of the story. So that's a good thing to know. Then in this process, that means according to the first law, Q plus W is 0. Which means that Q, the heat, is equal to minus W. So all I have to do is find where this Q is or W is, and then I would have found the other one. Okay? So this is a kind of an easy problem to do. Think about it this way. If the picture is correct, and I'm not saying that BF is always greater than BI, it could be the other way around. It could be compression. This is an expansion. Okay? It could be on an isothermal. This is called an isothermal, by the way. An isothermal line, I could go compress the gas. I don't have to basically expand it. So the V final could be less than the V initial. So in the picture, I drew it this way, but it doesn't have to be. You guys understand this point? This is just an illustration. So in this picture, if it's correct, okay, for doing really an expansion in an isothermal process, W is going to be work done. W is going to be negative. According to this expression, if W is negative, Q better be positive. Because if I add the two of them, they will give me 0. Because there is no change in temperature, there is no change in energy. So in this case, the heat must be positive. Okay? That is critical for this process in here. Okay? So all I have to do is find W. Once I find W, I'm in business. So let's do that. Remember, the temperature doesn't change. The temperature is the same at any given point on this isothermal. So PV equal to nRT can be written as an nRT over V, where both N and R and T, all of them are constant in this line. N is constant, R is constant, and T are constants, all of them. The reason why the last one is constant is because of the fact that I'm dealing with an isothermal, this process, okay? I'm going from A to B. So then the work then, W, is going to be the integral from V initial to V final of P dV, where P is equal to nRT over V dV, where N, R, and T all constants, though they come out of the integral, and the work is going to be negative nRT, the integral from the initial value to the final value of the volume of dV over V. So I have to do this integral now. Now I ask you, what is the integral of dx over x? Which function, if I take its derivative, I find 1 over x? You can Google it, you can look at your book of mathematics, you can. What is the antiderivative of 1 over x?
Is it ln?
Do you guys agree?
Yeah.
That's it, or there is no something else that I need to add to it?
Plus the constant C.
Plus 299,792,458 meters per second. Correct? Who said C?
Well, I mean like as an arbitrary constant.
Oh, you don't mean the speed of light. Okay,
Yeah.
good. Okay. You had me worried for a second. Okay, the constant c. Okay. Every time your calc instructor puts that c there, it makes me wonder why they do that. Okay, plus a constant c. Okay, good. But this is a bounded integral, so the value of the constant in the upper limit and the lower limit will cancel out. So at the end of the day, this will just be minus nRT ln of v evaluated between the initial value and the final value, and that is going to be ln of vf minus ln of vi. So w is equal to minus nRT ln of vf minus ln of vi. And there is an expression, if you guys remember from your the properties of the ln of A minus ln of B is equal to ln of, you guys remember that expression?
A divided by B.
Correct. So this can be written as minus nRT ln of VF over VI. Okay, so we have done enough in here so that we can find what the work is now in general for this process only, okay? We didn't do it for everything else. Minus nRT ln of the final volume over the initial volume. The way that I drew it in here, clearly VF is greater than VI, so this number is more than 1. So that means the ln is more than 0, which means that this number is positive, the T is positive, R is positive, N is positive. So indeed, W will be negative, okay? If it was the other way around, if it was really a compression, not an expansion, then in that case, the ratio will be negative. I mean, the ratio will be less than 1, and the ln of a number that is less than 1 is going to be a negative, times the negative is going to be a positive. So it takes care of the sign on its own, okay? So the argument I was making earlier about the drawing is correct in a sense. If VF is indeed more than VI, the work is going to be negative, which means that the heat in this case is going to be simply equal to positive because it's equal to negative W. And the negative times negative is going to be positive nRT ln of VF over VI. This expression is important for this process. This expression also is important for this process, except this expression will be very useful later on also when we talk about another quantity that is also state variable, namely the entropy. So I want you guys to remember this expression for the heat. So we found the heat, we found the work, and if indeed you add them both, you're going to get 0, because that's how we ended up with them. Does this process make sense to you guys, the isothermal process?
Yes, it does.
Yeah.
Okay, very good. Okay, another process of interest to us, I'm going to draw the second process in here, which is kind of easy also, which is called an isovolumetric. I don't like this word. I use the other expression that is commonly known as the isochoric process. This is where delta V is equal to 0. There is no change in volume, which means immediately that W is 0. Because remember, dW is equal to minus PdV. And if this thing is 0, this thing better be 0. Okay? And if W is equal to 0, that means delta U is equal to Q only, period, end of story. So this process is easy. You don't have to work for W. You already know what W is. It's 0. So the only thing that worries you is finding the change in the energy, which is going to be a Q. Now, let me draw this thing so that you can see what I'm talking about in here. So you have the V, you have the P, you have this volume, which is the same final volume. So this is the initial pressure, this is the final pressure, and the volume is the same because delta V is equal to 0, or dV is equal to 0. There is no change in volume. So this is a process that is an isochoric process. This is where W is equal to 0, and this is where delta U is equal to Q. So shooting straight up like this is going to be a an isochoric process or an isovolumetric process, namely there is no work involved. Now, a word of caution about this process. If indeed the final pressure is higher than the initial pressure, that means the final temperature, TF, is higher than the initial temperature, TI. That means the energy went up. That means you heated the system at constant volume. This is exactly how your what is that thing there? The pressure cooker works. This is how what you do with the pressure cooker. You first of all fix the volume and then you turn on the heat. And the heat is going to result in an increase in temperature in this case, and the pressure also. So this is a process where delta U is equal to Q. Remember, delta U is always NCV dt. Delta T, I should say. So in this case, Q is equal to NCV delta T, where delta T is simply the final temperature minus the initial temperature. So that's how much heat is. And that's how much actually work is, how much change in energy is. There is no work in this process. W is equal to 0. So this process is easy. Now, if the final temperature is less than the initial temperature, then in this case, Q is negative. You extracted heat actually at this process, and you lowered the energy. That's the same thing. If the picture is reversed, okay? So the way that I drew it somehow suggests that I'm adding heat to the system. So this is my Q. If indeed we're going this way, okay? If it was not, if we're going in the opposite direction, that we are extracting heat this way, okay? That's it. So an easy process, isn't it?
Yeah, pretty simple.
Okay, very good. So let's talk about another process that is a little bit kind of easy, which is the isobaric process. Remember, I promised 4 processes. This is the third one of them. This is where delta P is equal to 0. There is no change in pressure. This is a little bit more complicated than the first one, than the second one. So let me draw it a little bit. Again, we're going from on the PV diagram. So we have the volume, we have the pressure. The pressure doesn't change, but we're going from an initial volume, the way I'm drawing it in here, to a final volume, the way I'm drawing it in here, and in such a way that the temperature also changes, okay? So this is the final temperature, this is the initial temperature, where the temperature always satisfies PV equal to nRT. Although the pressure is the same, the volume has changed. So the temperature, because the final volume is higher than the initial volume, must be higher than the initial temperature. So the final temperature, TF, which satisfies the equation P times VF over NR, is higher than the initial temperature, the way I drew it again, P times V initial over NR. I'm assuming that the pressure is the same in this case. It's not changing. That's what isobaric process mean, okay? Obviously, the change in energy in this case, delta U is going to be NCV delta T. I'm going to find the work quickly in here. The work is going to be an easy calculation, actually. The work is going to be the integral from the initial volume to the final volume of PdV. But this process, the pressure doesn't change. So the pressure comes out of the integral because it is an isobaric process where the pressure is the same, maintained the same. So W is going to be minus the P, the integral from the initial volume to the final volume of dV. And what is the integral of dx? What is the antiderivative of 1, basically? Which function, if I take its derivative, I find 1?
It's just x.
X only?
X plus the arbitrary constant.
Okay, see, okay. Remember, this is a bounded integral, so at the end, that constant doesn't matter at this point. The reason why I'm throwing it is because there will be a case where it's going to matter, okay? So don't lose sight of that. So it's going to be minus P times V evaluated between the initial value and the final value. And that is going to be minus P times VF minus VI. And in a sense, this is how much work is. So work is going to be minus P times the final value minus the initial value of the volume. That's it. Because P is the same. That's why it comes out of the integral. So at the end, it's just minus P times delta V. Obviously, the way I drew it right now, V final is more than V initial, so this difference is positive, and the work is indeed negative. Okay? So somehow, I'm losing energy in the form of work, so I must be getting heat added to the system, or depending in this case, because of the fact that delta U is positive. Remember, TF is positive, okay? So let's write the expression now for the first law. So it says we need to find what Q is. Delta U is equal to Q plus W. This means that Q in this case is equal to delta U minus W. The W has a minus in it, so the minus 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 is going to be positive. So Q in this case is going to be delta U minus times minus P times VF minus VI. Whereas this quantity is equal to NCV times TF minus TI plus P times VF minus P times VI. I wrote it this way for a purpose. I already took that P and basically distributed among this difference. So this is how much heat is added to the system in here, because there is something that I'm going to pull out of this thing in here. So P times VF, it's NR TF. That's what VF is. And P times VI, it's NRTI. So this is NRTF. And this is NRTI. So NR is the same, so it's going to come out of this. So I have NCV delta T, which is TF minus TI, plus NR times TF minus TI. I have a TF minus TI as a common factor, so what I have Q is equal to N times, I have also N as a common factor, CV plus R times TF minus TI. It looks awfully similar. It looks similar to when we did this process, the isovolumetric process, and we found the heat Q to be NCV times TF minus TI, the final temperature minus, except I have N in both expressions. Here is N. I have the final temperature. What is it? The final temperature minus the initial temperature. Here it is. But instead of having CV by itself, I have CV plus CR plus R. I'm going to call this one CP. This is the specific heat at constant pressure. Having done it this way, then the heat in this process can be written as N, and this is a molar, by the way, per unit mole. The reason why it's molar is because I have to multiply by M by N in this case, times TF minus TI, where CP from this expression is clearly equal to CV plus R. This is a very important expression too. So I have a relationship between the molar specific heat at constant pressure and the molar specific heat at constant volume, and that constant R, which is 8.314. Okay. So we found the heat. So you're asking what is the heat? It's NCP times delta T. We found the energy, which is NCV times delta T. And we found the work, which is minus P times the final volume minus the initial volume. Found everything for this process. I called it a little bit more involved because it introduces a new concept and that is the molar specific heat at constant pressure. I'm going to introduce a new constant called gamma, and gamma is by definition the ratio of Cp over Cv. So this is the ratio of molar specific heats. It's clearly from this expression Cv over Cv is 1 plus R over Cv. 1 plus R over Cv. In other words, if I know gamma, I can find Cv because R is constant. And if I find Cv, I can find Cp by multiplying by gamma. That's all. So gamma is a number that has no dimensions. It's a ratio. It has no units. As a matter of fact, let's go back into what we introduced last time. For a monoatomic gas, Cv was equal to 3 over 2R. Then Cp, 3 over 2R plus R makes it equal to 5 over 2R. In gamma, it's going to be 5 over 2R divided by 3 over 2R, which is going to be 5 over 3, or 1.67. This is for a monoatomic gas like helium, argon, or neon, any of those gases, okay? For a diatomic gas, Cv, we added 2 degrees of freedom, if you guys remember, was 5 over 2R. And if I add another R to 5 over 2R, I will find that this number is 7 over 2R, which means that gamma cancel the R and the R cancel the 2 in the denominator. You will end up with 7 over 5, which is exactly 1.4. And this number is what is used for the actual engine in your car, because it's the air fuel mixture that goes into the car, and it's mainly air. And the air is mainly nitrogen and oxygen, although the one that reacts with the fuel, which is mainly benzene, in this case is going to be the oxygen, but it's both of them, which is 1.4, because it's a diatomic gas. So that is what we use for calculations for a gas, whether it's diesel or a regular engine, a regular gasoline. That's what we use. We use 1.4, okay? Because 7 over 5 is exactly 1.4. Now for a polyatomic gas, so this is case in point, for example, neon, neon, N2, O2, or air, okay? The polyatomic gas, anything else. The number, typically, I'm gonna go straight out into here, it's about 1.3. About, not exactly, might be slightly more or slightly less, okay? About 1.3. So in this case, if you're curious trying to find what Cp is, since you know what gamma is, you can find what Cv is. Subtract 0.3 from this number, subtract 1 from 1.3, you will end up with 0.3. That is R over Cv, which means that this number is going to be R over 0.3, okay? Or roughly about 3.333 repeating. So this is going to be 3.33 repeating times R. And this number, add to it another one, so it's going to be roughly about 4.3 repeating times R. So that is how much Cp is for polyatomic gas. Obviously, quantum mechanics comes into this picture in here, and you have all kinds of other oscillations to explain what's going on in that gas. So this is so far what we have seen, 3 processes: the isothermal process, the isochoric process, where W is equal to 0, the isothermal process where delta U is equal to 0, and the isobaric process is nothing is 0. Everybody is present. Delta U is not 0, W is not 0, and Q is not 0, okay? Everybody is there. There is another process, the 4th process that I promised that we were going to do, and that process is called the adiabatic process. Have you seen this process in chemistry? Anybody?
Not that I remember, no.
Okay. Okay, that's fine. So adiabatic process, by definition, Q is equal to 0. This is a poor definition of this process. We're going to see a better definition down the road. It's called actually isentropic process. Why it's poor? Because it involves a non-state variable. It involves the heat, and heat is not a state variable. All of this definition so far, isothermal process, T is constant, and T is state variable. Okay? Isovolumetric process or isochoric process, V is constant. That means delta V is 0. Okay? That is also state variable. Isobaric process, P is constant. That means delta P is equal to 0. So now we are introducing another process where there is no heat exchange, basically, because it's not a state variable. So you cannot call that heat is constant. That is not correct. Okay? There is no heat exchange, but the entropy is constant, actually. The entropy from the beginning to the end is constant. Since we don't know what the entropy is, this will be the next definition once we introduce that concept. Okay? So at this point, we're going to call it where Q is equal to 0. So that's an easy process also to absorb to some extent, because of the fact that Q is equal to 0. That means delta U is equal to W. If you find W, you have found what delta U is, because Q is 0. Okay, so this is basically what this process is. Except in this process, PV equal to nRT is a little bit complicated. It involves everybody. It involves the change in pressure. It involves the change in volume. It involves the change in temperature. Everybody is changing at the same time. That's what makes this process a little bit more complicated. But if I want to find the infinitesimal change in energy, then in this case, I can say du is equal to dw, okay? Where du is ncv dt, and dw is minus pdv. That's what we found earlier. Now, everybody is changing, even this p is changing. So you cannot just integrate and find everything in here, no. So we're going to find an expression now that eliminates this p from the process. And that expression is this one. So we're going to plug in this value of the pressure, which is nRT over V. That's it. That's what the pressure is. And now we move this expression to the other side. And we should be in business. By the way, this is delta U. Delta U is NCV delta T. And that is W. So we computed them if we know the initial value of temperature and the final value of the temperature. That's a problem. If we know TF and we know TI, we have found what the delta U is and W is. That's the only difficulty with. Sometimes they give you the initial pressure and the initial volume and the final pressure and the final volume, but you don't know what the temperature is. You have to find it because it's not as simple as PV equal to nRT. And then I should say, no, it is, okay? But if they give you all the values, if they don't give you all the values, you have to find them. If they give you the initial value and the initial pressure, but they don't give you the final values, they just give you the final volume, then in this case, you have a problem. That's why you need to find how P is a function of V, or how T is a function of V, or, this is an or, not you have to, or how T is a function of P. This is in a PV diagram, this is in a TV diagram, and this is in a TP diagram. So depending on which diagram you're processing, typically this is what we work with. So we need to find how P depends on V, really. That's really what we're trying to find now. So move this to the other side, of course, the negative sign becomes positive. So I'm going to have NCV dt plus P, I'm going to sub it by its value, nRT dV over V equal to 0. From here, it's clear that the N cancels from both sides, and that's it. So what I have in here, I have CV dt plus R times T dV over V. I would love to integrate this expression, but it's not ready for integration yet, okay? let's finish this point and we're going to meet next time to do more applications of these concepts. So what I'm going to do is divide by CV times T. If I divide by CV times T, I will end up with an R over CV in here, and it will end up with a DT over T in here. Remember, the CV cancels this CV. So divide by. So we're dividing by this expression. So this CV cancels that CV, but the T stays in the denominator, plus R over CV times the T cancels this T, so I'll be left with dV over V equals to 0. We're almost ready for the integration. The only problem is, what is this R over CV? This R over CV is just gamma minus 1 from this expression. R over CV is just gamma over minus 1. So this is gamma minus 1. So what I have really, dt over t plus gamma minus 1 times dv over v is equal to 0. Now I'm going to integrate. Well, dt over t, we saw this one. That's just an ln of t in this case. Make sense? Yes?
Yes.
Yeah.
Plus gamma minus 1 times an ln of v also, that's the same thing. The integral of 0 is constant. That's why I was really after that constant earlier, after c, okay? Because I want you guys to remember that this is an indefinite integral now. I don't have any boundaries, so I better carry that constant with me. Otherwise, I have a problem in here. So then this one is actually ln of t plus ln of v to the power gamma minus 1 is equal to a constant. Okay? This, I just took the power in here. This is the properties of the natural log. The last thing in here, I can combine the ln plus ln, which is the ln of the product of tv to the power gamma minus 1 is equal to a constant. We're going to take the exponential of everybody, and the exponential of the ln is just the expression under the argument of the natural log, which is tv to the power gamma minus 1 is equal to the exponential of a constant is another constant. Exponential of 12 is some big number, okay? So whatever that number is, it's just another constant, okay? So here is the problem. We have a relationship how the temperature and the volume depend on each other. But as I was saying, I really don't like this one. We have a TV relationship, which is fine. I really want the PV relationship because that's what I typically work with in PV diagram. So this would work. And this is part of the lab, by the way. You're supposed to show this one part of the lab. Once you find one, you can find any one because of the fact that, remember, PV equal to nRT. So I'm going to get rid of this T in favor of this P. That's all. So this T here is equal to PV over nR, and plug this expression in there. So what I have in here, I have PV over nR times V to the power gamma minus 1 is equal to some constant, okay? Some constant, who cares what that constant is? I'm gonna multiply everybody by nR, which brings me to another constant, a new constant. And now you're probably wondering, what is this constant business meaning? And that's part of the lab, by the way. You relate all of your constants together. But we're going to do this quickly. Well, PV times, I have V times V to the power gamma minus 1. This is as if V to the power positive 1 cancels the negative 1. So this is V to the power gamma, and I have the pressure P in here. So indeed, I have found P as a function of V. P as a function of V is simply some constant divided by V to the power gamma. So in the PV diagram, this is the expression I should be using, where gamma depends on what gas you're dealing with. If it's a monoatomic gas, it's 1.67. If it's a diatomic gas, it's 1.4. If it's a polyatomic gas, it's roughly about 1.3. So that is what that gamma is. Now, what that constant mean is the following. So let me explain this point, and we're going to be done. So this is the V, this is the pressure. I have, this is the starting point A that has all of your nice features, including the initial pressure, the initial volume, I should say, and the initial pressure. And this is the point that you would want to end up with, VF in PF in this process, which is called an adiabatic process. Which means Q is equal to 0, that's all, okay? Throughout this entire process, PV to the power gamma is constant. So how much this constant is? If I know this point, if I know the initial volume and the initial pressure, then this is the initial value of the pressure times the initial value of the volume to the power gamma, that's it. That's all is that. If I know the final values, then this constant is the same, because it's the same constant throughout the entire adiabat. That's why it's going to be PF VF to the power gamma. As long as I know one of the points, that's it. I know what that constant is. So it's really no big deal, honestly. Okay. Okay, I think we have covered a lot of materials. We've covered all the 4 processes. We discovered the first law of thermodynamics. We still have another point of discussion, so please do not start putting your inputs yet until the end of the week, which is Wednesday, because we will do examples on Wednesday, on Thursday when we meet. On Thursday, we will do more problems. And I'm going to go through those problems, and I want you to also throw in the numbers in those problems. So don't do yet. So right now, the first item of debate is basically just to put the first law in your own words, but don't do it yet, okay? Do not start putting this question yet until comes Thursday when you put these things. We discovered the isothermal process. We discovered the isochoric process. We discovered the isobaric process, and we discovered the adiabatic process. And we have found everything that has to do with their energies. I mean, they're changing energies, the work associated with them, the heat associated with them, including the curve, how it looks like. This is the last expression, is how the curve would look like, which is just a constant divided by the volume to the power gamma. Gamma is more than 1. So this drops more rapidly than the isothermal. That's why it's called the adiabatic precipitation, because it goes so fast. That's why when you're doing chemical processes or physical processes and the process is so rapid, then in this case you're dealing most likely with an adiabatic process. Okay, sounds a lot, doesn't it?
Yeah, a little bit.
Okay, so the good thing is we covered all the processes that we need. Granted that these are not the only processes out there. There is an infinite number of them, but these are the documented ones that you're going to be doing calculations with. Any given process can be the combination of one or more of these processes. And if the process is not one of these processes, it should be easy to integrate. It should be easy to find the area, because that's what the work is. It's the area under the curve. That's all. That's what we've been doing all along. Okay. When we meet on Thursday, we'll do applications. So do not answer discussion number 3 yet, this question of week 3 yet, until Thursday, because then you should be ready to do the whole thing. Sounds good?
Sounds good.
Sounds good.
Okay, very good, everybody. So I'm gonna stop recording, and I will see you Thursday.